And these white data points show a tight mass N2O relation to exist. And so what we see from these two plots then is that star formation rate mostly seems to impact upon the oxygen abundance specifically. As such, the fundamental metallicity relation shown on the left is commonly understood as reflecting variations in the rates of gas inflow, with an increasing gas inflow boosting the star formation rate while also diluting the metallicity due to these inflows being metal poor, thus producing the three-way relation that we see. Looking to the final figure then, we now see the N2O metallicity relation, with mass tax again shown in white and mass SFR tax shown in color. And in this case, so a few things to note. On one hand, at high metallicities, we see a very tight N2O metallicity relation, whereas at low metallicities, we instead seem to have an approximately fixed N2O, so an N2O plateau at low metallicities. The fundamental metallicity relation is also apparent in this final plot, with high star formation rates seen in the bluer colors appearing to be associated with higher N2O at a given metallicity. With that said, though, a better way to view these blue points here is that they have low metallicity for their N2O abundance, since we can see from the other two plots that SFR primarily affects metallicity rather than N2O. So at this point, we should consider how we might interpret the N2O metallicity relation. And to do that, we should consider how we expect chemical enrichment in galaxies to proceed over time. A common assumption is that at early times, nitrogen and oxygen are released at a roughly fixed ratio by massive stars, resulting in a rising metallicity over time along with this N2O plateau. Later on, low to intermediate mass stars begin to die, and they inject increasing amounts of nitrogen into the interstellar medium, producing this tight N2O metallicity relation at the high metallicity end. I should note that this is not the only interpretation of the N2O metallicity relation, though it is indeed a very popular picture to consider. In any case, so far I've talked specifically about metallicities in galaxies across global scales. And it is also interesting to consider how gas metallicities and gas abundances in general vary within galaxies. And for this, we can make use of integral field spectroscopy, with the MaNGA survey being a particularly large and useful survey for this kind of thing, done relatively recently. So MaNGA obtained integral field spectroscopy of roughly 10,000 nearby galaxies, with all data publicly available as of data release 17, along with all associated data products. I'm showing an example MaNGA galaxy down below, where we can see an image cut out on the left, along with a line of sight velocity map in the middle and an H-alpha emission line flux map on the right. Now, every little square on the middle and right panels is a spaxel with its own associated spectrum. And with these spectra, we can proceed to map a large variety of galaxy properties relating to both their stellar populations and also their gaseous components. Key for the research I'm going to be presenting is MaNGA's ability to map the fluxes of a large variety of emission line features, which in turn provides us the ability to map abundances across large samples of nearby star-forming galaxies. And so with MaNGA, we can probe gas abundances within galaxies in two key ways. We can look at radial profiles, as for instance shown on the left, and we can also look at local relations across very large spaxel samples, as for instance shown on the right. And so in the next few minutes, I'm going to go through both of these aspects before then segueing into my own research. So starting then with gas abundance profiles. On the left-hand side, we can see mass-tacked metallicity profiles for a MaNGA galaxy sample. Specifically gas metallicity versus galactocentric radius normalized by the effective radius for the different mass tacks, with the right-hand side showing a very similar plot but for the N2O abundance instead. First thing to note here is that if we look at the metallicity figure, we can see that generally the metallicity falls with radius, which is consistent with the expectations of inside-out galaxy formation. But we can also see that the profiles are flattening at the lowest masses, potentially indicating additional physics relevant to these low-mass systems. We can also see a flattening in the gas metallicity profile at the highest masses, which does not have a corresponding flattening in the N2O profile seen on the right-hand side. And this is potentially telling us that a metallicity equilibrium has been reached in the inner parts of these massive star-forming galaxies. Another way we can look at these profiles, though, is to consider the N2O and the O2H together. And that's what we're seeing now on the left-hand figure. So again, we have mass-tacked radial profiles now plotted in N2O metallicity space, with each line going from the centers of the stacks out to two effective radii. Again, we see radially declining abundance profiles for all but the most of the massive galaxies, really, for every stack aside from the least massive stack. But we also see that the higher mass galaxies appear to be offset to higher N2O at a given metallicity, which is really the biggest intended takeaway from this particular figure. For interpreting this, variations in star formation efficiency can provide a potential explanation for this result. With the inner parts of the most massive galaxies expected to possess greater star-forming efficiencies than the inner parts of the least massive galaxies. And so when star formation efficiency is very high, we expect gas metallicity to shoot up at early times, with the N2O remaining constant during that period, with N2O then beginning to rise with metallicity at a comparatively high metallicity value. Instead, if star formation efficiency is particularly low, then we expect the metallicity to rise relatively slowly at early times, resulting into the N2O then beginning to rise at a relatively low metallicity, once low to intermediate mass stars begin to make significant contributions. So that then is radial profiles. But another thing we can do with MaNGA is to consider local relations across many, many galaxies by combining them into really large spaxel samples. And that is what we're now seeing in these two plots. Starting from the left, then, we have the local gas metallicity plotted against the local stellar mass surface density for a sample of more than 500,000 star-forming MaNGA spaxels. And we see from this figure then that the local metallicity rises quite sharply as a function of the local surface density, similar to the mass metallicity relation I presented earlier on. An additional stellar mass dependence is evident here, however, as can be seen on the right-hand side. So in this case, we again have metallicity plotted against local surface density, but now with these colored data points indicating bins in stellar mass. And what these points tell us is that at a given local density, more massive galaxies in terms of stellar mass are associated with higher local gas metallicities, indicating the existence of a three-way mass density metallicity relation. But we can, however, take this even further, and various previous studies have indeed taken it further. With one study in particular being Huang et al. 2019, who used the mass density metallicity relation to predict metallicities and then compare predicted metallicities with the actual observed values. So on the left, just as a reminder, we have the mass density metallicity relation, whereas on the right-hand side, we have the observed minus predicted metallicity divided by sigma z, which is the standard deviation of offsets. And this is being plotted against the local H alpha equivalent width. Now, high equivalent widths are associated with greater star formation activity. And what this plot is therefore telling us is that when the star formation activity is particularly high, we are likely to see metallicities lower than what the mass density metallicity relation would predict. This particular result is something I'll come back to rather later in this talk. But for now, the overall takeaway from all this should be that local gas metallicities are very strongly linked to both local and global galaxy properties. Now, given the connection between star formation and chemical evolution in galaxies, we naturally expect a connection between the chemical abundances we observe and star formation histories within galaxies. Spectral indices provide a model-independent means to characterize star formation history in galaxies, with the principal component analysis method providing an approach which is good at lower signal to noise values than traditional absorption line indices. The PCA method was applied to the MaNGA sample back in 2018 by Kate Rowlands and team. And we can see some examples of how this works in the two figures below. First of all, I'm showing a large MaNGA spaxel sample plotted in terms of the first two principal components, with these two components relating to the 4,000 angstrom break strength and to the strength of Balmer absorption, respectively. And based on where spaxels fall in this parameter space, they can be classified based on their star formation history, with classifications including star forming, green valley, post-starburst, and starburst. But on the left, this has a good 1,000 or so galaxies included, and so it's not really clear how this is going to look for any individual galaxy. And that then is why I'm also showing an example for just one particular galaxy on the right. And what we see here then, we have an image cut out on the left, and on the right, we have the corresponding PCA map for this particular galaxy. Unsurprisingly, this particular galaxy is dominated by star-forming regions. But we can also see some localized starburst regions associated with the bright blue spiral arm features on the image cutout. And as part of their analysis, Rowlands et al. Did specifically consider gas metallicities when presenting their findings. And this plot here shows their key results in this regard. What this particular plot is showing is, again, radial profiles for galaxy stacks, profiles of gas metallicities, with the stacks in this case being by stellar mass and by PCA classification for a sample of low asymmetry galaxies. What we see in this case then is that starburst regions typically possess reduced gas metallicities at any given radius, with post-starburst regions typically being between the starburst regions and the ordinary star-forming regions. Green Valley regions, lastly, are typically more metal-rich at any given radius, particularly for lower mass galaxies. We can learn a whole lot more, though, by also considering nitrogen in this picture via the N2O abundance, due to the much longer timescales in which nitrogen enrichment takes place. So, right, so this brings us to the paper I'm going to be focusing on for much of this talk, in which we wanted to investigate the impact of local star formation histories on N2O and O2H abundances. And in order to do that, we were going to need data from a good variety of sources. For the abundances themselves, we used the MaNGA data analysis pipeline maps to obtain maps of emission line fluxes, which could then be used to estimate abundances. For maps of stellar properties, meanwhile, we made use of the MaNGA Pipe 3D maps, obtaining maps of the D4000 index amongst other properties. For global galaxy properties, most importantly stellar masses, we made use of the NASA Sloan Atlas catalogue. While for star formation history classifications, we went and used the MaNGA principal component analysis maps, which I should note are updated from as originally presented in Rowlands et al. 2018. Next, we'll look briefly at how exactly the abundances are being determined in this particular study. And in both cases, we used strong line calibrators determined via electron temperatures, the so-called direct method, in order to calculate our abundances. On the left, we see the calibrator used for gas metallicity, in which we see the RS32 metric, involving sulfur, oxygen, and hydrogen, plotted against the gas metallicity. In this particular plot, the green data points are individual galaxy spectra, whereas these larger circular points are stacked spectra, which were stacked based on emission line properties, with this stacking being necessary because the direct method becomes increasingly difficult at higher metallicities. This then is the calibrator for gas metallicity. And on the right, similarly, we see a direct method N2O plotted against the N2O2 metric, in this being from a nearby sample of individual star-forming galaxies, with the black line representing the calibration used in their paper and hence in our particular work. These calibrators, I should note, were chosen for their independence, in order to avoid overlap in emission lines used to determine gas metallicity and to determine the N2O abundance. Although, due to the need to correct for dust reddening, H alpha and H beta are implicitly involved in both calculations. Right, so I'm now going to go ahead and show my final spaxel sample, which consists of more than 1,000,000 spaxels over nearly 2,700 MaNGA galaxies. All of these were selected to display star-forming emission as is standard for gas abundance work, meaning that when I refer to them by their classifications from PCA, I am specifically referring to their stellar populations. On which note, we went ahead and classified the spaxels using the PCA in the manners shown in the below two plots. With the spaxels then split into subsamples based on these classifications, with the classifications specifically being used being star-forming, starburst, post-starburst, and green valley. Right, so getting into results now then. And first of all, I'm showing our star-forming subsample in N2O metallicity space, represented with these black contours, with the full sample shown underneath in with individual plotted points and with these color maps. And as expected, the star-forming spaxels are showing a really tight N2O metallicity relation. In order to quantify this relation, we fitted this purple line to the star-forming spaxel subsample, with the fit consisting of a straight line fit at higher metallicities along with a fixed N2O plateau at lower metallicities. And this line will also be included on subsequent figures in order to compare other subsamples with the star-forming spaxels as well as to just generally guide the eye. So for the other spaxel classifications, for the starburst, post-starburst, and green valley spaxels, we selected control samples of star-forming spaxels by matching on local galactocentric radii and on global galaxy stellar masses. And we can see an example of how this works for the starburst spaxels down below. In this case, then, we have the N2O metallicity relation plotted with yellow contours representing the starburst paxels and grey contours representing the corresponding control sample. And with this plot, then, we immediately arrive at the first key result, which is that starburst paxels show diluted abundances relative to their controls. But if we instead look to the post-starburst paxels over on the right, we can see that they, in purple, behave far more similarly to their own control sample, which is shown here again in grey. Potentially most interesting, though, is that both the starburst and post-starburst paxels follow essentially the same N2O metallicity relation as the star-forming paxels do, which we can see both from comparing the behavior of the contours and also by looking at the behavior of the purple line, which is pulled directly from the figure I showed a few slides back. For the star-forming spaxels. In terms of interpreting this, then, our favored interpretation is that local starbursts are triggered by metal-poor gas infall, resulting in these spaxels typically possessing lower abundances than ordinary star-forming spaxels. And in this picture, a transition to post-starburst can then be expected over a few hundred megayears, with chemical enrichment continuing over that time and producing the behavior seen on the right-hand plot. And this then results in a situation where late-time abundances are largely insensitive to the precise shape of the star formation history. Or to put it another way, late-time abundances are largely insensitive to the stochasticity of the star formation histories. Turning now to the Green Valley spaxels. I'm once again showing N2O metallicity relation, now with the Green Valley spaxels in green and their own control sample in grey. And in this case, we can see that the Green Valley spaxels display elevated N2O at most metallicities. This does, however, seem to be a general feature of the older spaxels in this dataset, which is the point of the right-hand plot. So what you're seeing in this case is the median D4000 plotted in small bins of N2O and metallicity, with higher D4000 being associated with older stellar populations. And since we see this red blob towards the top of the plot, what this blob is telling us is that it is at high metallicities and elevated N2Os where the oldest paxels are typically found. And for this, we have two favored explanations. Those being that either these paxels are experiencing a reduced star-forming efficiency, resulting in N2O having rised at relatively low metallicities, or alternatively, these paxels are the result of recent rejuvenation by metal-poorer gas, pushing down the metallicity while not pushing down the N2O nearly as much. So going back then to this pair of plots I showed rather earlier on, in Huang et al. 2019, there was a specific focus on so-called anomalous low metallicity spaxels, with these spaxels being those with metallicities significantly lower than what would be predicted from the mass metallicity density relation, with these ALM spaxels shown in blue on the right-hand plot. Now, since these spaxels do seem to preferentially be found in regions of high star-forming activity, it was suggested in this paper that ALM spaxels are the results of recent localized metal pore inflows, similarly to what I just argued for the local starburst regions in our own sample. And Liu et al. 2021 took the idea of ALM spaxels further by looking at their behavior in N2O metallicity space. And we see the key result from that paper on the right-hand side, where we have ALM spaxels shown in yellow and a sample of non-ALM shown in purple. And we see that the ALM regions display reduced metallicity for their N2O. The green arrows in this particular figure show the results of a toy model in which metal pore gas inflow serves to dilute the chemical abundances. And we can see in this model that the inflows are expected to preferentially reduce the metallicity compared to the N2O. Suggesting then that metal pore inflow can explain the differences seen between ALM and non-ALM regions in N2O metallicity space. But this, however, at least at first glance, presents a bit of a problem because I've already said we think local starbursts are due to metal pore inflows. But while local starbursts do show diluted gas abundances, they also seem to follow basically the same N2O metallicity relation as ordinary star-forming regions, while ALM regions are clearly offset. Now, while this does at first sound like a contradiction, it is important to note that local starbursts and local starburst spaxels and ALM spaxels are not, in fact, the same dataset. And we can actually reconcile these two findings quite straightforwardly if we remember that oxygen enrichment will proceed very quickly after a starburst takes place, which we can expect to result in N2O offsets being quickly enriched away after an inflow event happens, thus resulting in the difference between starbursts and ALM regions. So I'm going to spend a few minutes now on key takeaways, and these few slides will be a great place to jump back in if you got lost at any point in the last 20 or so minutes. The first key takeaway of the presented research, then, is that late-time abundances are largely insensitive to the stochasticity of star formation histories. And to see what I mean by that, we can first consider what a smooth star formation history might look like in N2O metallicity space, with metallicity rising at fixed N2O at early times, followed by a rise in both metallicity and N2O at later times. Whereas if we have a sudden metal pore inflow followed by an inflow-induced localized starburst, what we'd expect then is to first see the metallicity drop more than the N2O drops, but with the starburst then rapidly pushing us back onto the same N2O metallicity relation as before. And as this starburst region then develops into a post-starburst region, we expect progression to post-starburst phase over a few hundred megayears with enrichment continuing in that time, such that by the time we get to the post-starburst phase, we're at a very similar abundance to if the inflow had never happened in the first place. So this then is key takeaway number one. Key takeaway number two is the elevated N2O possessed by the older regions in our MaNGA dataset. And we believe there are two plausible explanations for this particular finding. On one hand, it might be that old regions possess a reduced star-forming efficiency, resulting in metallicity resulting in N2O beginning to rise at relatively low metallicities, thus producing an offset at late times. Alternatively, it could be that at least some old regions in our dataset may have been rejuvenated by recent metal poor inflows, with these inflows then preferentially reducing the metallicity over the N2O abundance. And thus then we have what I'd say are the two key takeaways from this particular study. Moving on then, for the final few minutes, I'm going to talk about an ongoing follow-up piece of work, looking at the N2O potential relation across MaNGA galaxies on global scales. In order to motivate this a bit, we can see on the right, a pair of aperture-matched samples from the Sohn Digital Sky Survey. And for these samples, we see the effective radius plotted against stellar mass, with these little bins colored by galaxies' gas metallicities. We see here a very striking trend across the mass size plane, with more compact galaxies being more metal rich at any given mass. And this produces a particularly strong correlation with metallicity and stellar mass divided by half-light radius. Now, since M over Re is often interpreted as a proxy for gravitational potential, this suggests possibly a direct link between the metallicity and depth of potential in galaxies. And we can again learn more here by considering N2O in this picture, due to the longer timescales in which nitrogen enrichment takes place. And that's what I wanted to look at using the MaNGA data. So I see I'm low on time, so I'll actually make this the final slide. So what I did was to construct, fit straight line profiles to a subset of the MaNGA galaxies between 0.5 and 1.5 effective radii, and then use the fitted value at 1RE as a characteristic value, both for N2O and also gas metallicity. We can see here the N2O plotted against stellar mass on the left, with N2O also plotted versus potential in the middle and global surface density on the right. And similarly to what's been reported for gas metallicity, we find the strongest correlations between N2O and potential. Looking also at what happens if we look at gas metallicity in this particular way, so these again being values at 1RE. While we do obtain very similar results for metallicity, it is interesting to note that N2O actually correlates very slightly stronger with any of these parameters than does the metallicity. How much time do I have?
You're on time, don't worry.
Okay, fair. I'll just keep going then. Okay, so right, so I've shown individually how N2O correlates with um um mass potential density along with metallicity, with Spearman rank correlation coefficients used to parameterize the strength of correlations, with N2O potential seeming the strongest. But something interesting comes out if we consider N2O and metallicity together when looking at um, global potential within galaxies. So what you're seeing here is the characteristic N2O plotted against the characteristic metallicity, with individual data points colored by the galaxy's estimated potentials. And by I, because N2O and metallicity are so tightly correlated, it is very hard to disentangle just how potential is relating to these two individually. But interestingly, if we perform a partial correlation coefficient analysis, the potential actually seems to be increasing almost entirely with N2O, with this black line representing the direction of greatest potential increase as determined by partial correlation coefficients. This can, however, be visualized much more cleanly if we apply 2D smoothing to the potential, which I've done on the right-hand side. And in this case, we can see that at any given metallicity, potential is rising significantly with N2O. Whereas if we look at any given N2O, the potential is very much not rising with the metallicity. Resulting in a picture then in which N2O depends tightly on gravitational potential, with the previously reported metallicity potential relation simply appearing as a byproduct of that. Yes, on that note, I shall leave my summary slides up, and I'd like to thank all of you for listening to me. Thank you very much.
Thank you very much, Nicholas. Very interesting talk. Thank you.
Thank you.
So we have some time for questions. Well, I have one question, and I would like to ask you what is the role of the merger, for example, and the presence of the outflows in the flattening of the metallicity in your sample?
Let's see. So flattening, it sounds like you're referring to this plot, right?
Yes. Right.
Okay. So yes, on one hand, so generally speaking, when you look at star-forming galaxies in MaNGA, your sample tends to be dominated by galaxies in relatively low environments. So when looking at the behavior across big MaNGA samples, mergers, certainly major mergers, you don't expect to have a significant effect at late times. On the other hand, outflows are expected to be very important in explaining the behavior of the less massive galaxies in these kinds of samples. In particular, explaining the flattening in the profiles seen on these kinds of plots. And this happens because for lower mass galaxies, gravitational potential is also going to be lower, and hence these galaxies are not especially resistant to losing metals via outflows. Whereas as we get to the higher mass galaxies, the escape velocities become much higher, and so it becomes much, much harder to lose metals via outflows. And this is a picture which has also been supported by chemical evolution modeling of MaNGA galaxies. With probably the best papers for this, there's a later Belfiore paper as well as a 2018 Barrera Ballesteros paper. In terms of going back to mergers, I should probably mention. So, while big mergers are unlikely to be relevant for the majority of spaxels in my sample, it was pointed out back in Huang et al. 2019 that, amongst other things, ALM regions are disproportionately likely to be found in asymmetrical galaxies, which does suggest that galaxy interactions play a role in sending low metallicity gas into the galaxies we're looking at, with potentially smaller scale equivalent processes, such as just capture of gas from the CGM, say, or infall of gas-rich dwarfs, then playing a role in the formation of ALM regions, but perhaps similarly the appearance of localized starburst regions seen in my own work. Hopefully that answered
Okay, yes,
question.
sure. Thank you. Well, there is a question here in the chat from Borja Perez. His microphone is broken. So he was wondering which is the driver of such inflows of metal poor gas. It has been reported for lyrics and urics to be merger events, but this will imply a larger metallicity dilution. On the other hand, for what understood, he said, oxygen abundances are estimated from a combination between sulfur and oxygen emission lines. Recently, it has been reported by Zamora and Diaz 2022 that the sulfur-oxygen ratio might not be universal as expected, and hence oxygen abundances estimated in this work might be affected by deviation on sulfur-oxygen ratio.
Okay, so these are both really good questions. I'll start with the second. So let's go here. So the oxygen abundances are being determined from a combination of sulfur, oxygen, and also hydrogen lines. So it's not like we're specifically converting between S2O and metallicity. With that said, let me think. So yeah, we're not converting between S2O to O2H to get these results. So I don't think I don't think issues with the S2O ratio would affect my findings, but this is certainly something I'll double check, and I would like to thank you very much for bringing that to my attention. Concerning the drivers of infalls of metal poor gas, I have touched on this already, but to maybe go through it more slowly. So on one hand, there will be galaxies in MaNGA which are highly asymmetrical and which have likely experienced recent interactions with nearby neighbors. And for such galaxies, we would expect that to be the drivers of infalls of metal poor gas. Whereas for the bulk of galaxies in our sample, which are, they're not going to be asymmetric, they're going to be in fairly low density field environments. For these, we expect similar but smaller scale processes. such as accretion of gas-rich dwarfs and also accretion of gas clouds from the CGM around the galaxies. Oh, well, thank you very much, Borja. I hope you get your mic.
So thank you very much from Borja. Yes.
Sorry, I butchered
Okay.
that pronunciation. I do apologize.
Don't worry. Well, I think if we don't have any other questions, I think we can stop here. Thank you very much, Nicholas, for the very interesting talk. And thank you very much, everyone, for joining us.
Thank you very much.
Thank you, Nicholas.
Where do I go? Right, there we are.